Hi, it's time for another math easy solution to discuss further into applications of integrals and look further into moments and centers of mass and go over the example 6 of the example series. And this example is basically what I'm going to do is go over the last example, example 5, and this is the example here. So in my last video I solved the volume of a torus using the theorem of Pappus and showed that, well, basically a torus is just like a donut shape, and I showed that if you had, let's say, a line like this, and you had a torus, let's say you have a circle like this, r, so it's radius r, and then you rotate this about this line, where the distance from here all the way to the center point is capital R, which is, well, big. It's greater than small r there. Yeah, and I showed basically if you were to rotate this to get a shape, let's say a solid shape, it would look something like, let's say, let's just draw this about. So you'll have some sort of donut shape like that, around like that. I'll just draw it in 3D. So basically this is a torus. It's just like a donut. A donut is a torus. So let's say you had this shape all the way around, and this has a volume V. So when I showed using the theorem of Pappus that the volume is quite simply going to be area of this region right here, so this circle like that you're rotating about, times by d, which is the distance that the centroid of this region, so this region, the centroid of this region is just the center, again, like I showed in the last video, so watch that for more in-depth analysis or more detail of covering this proof for this theorem. And then when you rotate, so the distance that the centroid travels around this line of rotation. So if you rotate this all the way about like that, and then the total distance this centroid travels is going to be d, and the volume which of this shape is quite simply a times d, which is the centroid or center of mass that it travels here. And in our case, well, the area of the circle, that's just a circle, is just going to be pi little r squared. And now the distance that this centroid or center of mass travels of this region, it's a circumference right here. So that's just going to be, this is just going to be, well, a circumference of a circle with radius r, capital R, which is the distance to the centroid. That's going to be, well, 2 pi r, like I showed before. So that's what we have. So we can solve for the volume of this torus very simply. That's going to be the area, which is pi r squared times by d, which is 2 pi r. And then just simplify this, we get pi squared, put the 2 in front, 2 pi squared, r squared, and then capital R like that. Circle that. So that was very simple, just applying the theorem of Pappus, which is basically the area of the region times the distance that the centroid travels when you have a shape that's formed like this. Yeah, so that was my last video, and in this video, this example we're going to do is, as a comparison, find the volume of a torus using basic integration technique. So instead of using this shortcut or this theorem of Pappus, which is really basically an easy way of solving shapes. So basically you can, when you're solving for any sort of region like this, you're rotating, always think if you can apply this theorem, because it will save a lot of time, as I will show right here. So if we were just going to use basic integration techniques, it's going to be much more difficult. So what we'll do is, first thing is draw the x and y axis like always. So we have something like this, x, y, and now to make it, to add this region here, the simplest case, what we could do is put it at a distance r from this, but on the x-axis. So we'll draw a circle like this. Okay, here there's a better circle like that. So then the origin of this is gonna be, I don't know why it's not drawing it. So this origin here is at the point capital R and 0. So that's that point, and this point here is gonna be, well, capital R plus the radius of the circle, which is R, and 0. And then the y is 0. And then here is gonna be, well, this is simply capital R minus R 0, because this total distance here is R, that's the centroid of the circle, and then from here, then from here to here is the radius of this small circle, that's R. Of the circle is R. So the addition, this one's a subtraction, like that. And now this circle right here, the equation of a circle is, like I showed before, and you see my video link below on the equation of a circle, it's going to be, in this case, x minus r, because the origin is shifted by r, so that we shift it over there, so it's going to be like this, plus, and again, make sure to watch my earlier video to see why it's like that, and then we're going to have plus y squared, because the origin is 0, equals 2 r squared, which is the radius of the circle. Yeah, now what I'm going to do is actually split this equation of a circle into, well, two equations, and I'll explain why in a bit. Basically, split the circle into two equations. And the reason is because a circle, if we want to function in terms of x or in terms of y, we gotta move things around. This is just a general function, and we're gonna write everything in terms of y. The reason is because we rather not deal with this x minus r and then squared, just because it's more complicated that way. So we want to do the easiest one possible. So what we'll do is we go to the circle equation, x minus r squared plus y squared equals to r squared. So we're going to write x in terms of, x as a function of y, just to get rid of this x minus r squared. So move this around and then square root. We have, what we end up having is x minus r squared is equal to, well, this is r squared minus y squared, square root both sides. What we end up having is it's a plus or minus, so this equals 2 plus or minus squared, because this x minus r could be positive or negative, and then when you square it, it becomes positive. So this has to be positive or negative. That's why we have two equations. So what we end up having is x equals 2r plus or minus, and then this is going to be r squared minus y squared. Yeah, so this is how the function is. So then the right side of the equation, so x equals r plus r squared minus y squared. This is the right side because, well, it's always greater than or equal to the left side, because you're adding this, and then it's always positive inside the square root. And this equals 2xr minus r squared minus y squared. This is going to be the left side of the circle. Yeah, and I'll just write that down here. So this left side is going to be like that. This left side has the equation. We'll call this actually x equals 2g of y, and then the right side is x equals 2f of y. Yeah, and going back here, I'll just write these as the functions here. So we'll write this is f of y equals 2, and this is g of y equals 2, the left side. So just to make it easier to write there. And now, as always with integration, we're going to have to find basically a small section or a small volume and then sum it up to infinity. And in this case, it's actually easiest if we took a horizontal slice like here. Let's draw it across like that, and let's say it cuts in like that. So we have this slice like this, and let's say at this top part, this is our yi, and then the bottom one, this is going to be our yi minus 1. And then the point here, this could be any point, and again, that's any point within the interval there, and what's called as yi star. So that's our sampling point, and this is basically the basic idea of integration. Always take a sample point like that, and you can learn more about this in my integration derivation videos. So now what we'll do is if we rotate this, because we want to rotate it by this to get a torus, we rotate. And then what we end up having is something that looks like that. Let's just draw it. And then the top part, let's draw this a bit neater. So we end up having something that looks like that. And then it's in 3D, so it's a 3D section like that. And then let's draw this in 3D. All the way around. So now we have a a ring like this. And this ring we'll call this Vi. It has a volume Vi, and you can calculate this volume. And yeah, now the distance from this point all the way to here, the sample point, we'll draw it like that. It's going to be, well, this is on the left side of the equation, so we'll write this as g of yi star. And then all the way to this right side here, this is gonna be, let's just draw this line like that, all the way down here. This is gonna be f of yi star, and we could use this in calculating the volume. Yeah, so now when we look at to calculate this volume of this section, and again over here it has a delta y height like that. So yeah, now we can calculate this volume as, and I'll explain further in a bit. Basically, we can write this as of that subsection Vi as equaling to the volume of the outer circle minus the volume of the inner circle. So this is gonna be f of, so pi r is basically the area is pi r squared times delta y, and I'll explain this in a bit. So we're gonna have pi r star, the sample point like that, squared, and then times this by delta y, and then minus pi, the radius of the inner circle, g of y star squared, and then delta y, and then this equals 2. Actually, before I get to that, and the reason we're having this is because if you look at, let's say, the big circle, let's just draw this in 3D. So let's say you have it in 3D like that. So this has a delta y, and then the distance from here to here is going to be our f of yi star, which is simply distance from here all the way here. So this is up to f of yi star. Then what we have for this section, volume of this equals to simply the area, which is going to be pi times radius, f of yi star squared, and then delta y, so that's the height. And then so what we do is subtract, so subtract from, and then if we were to draw this straight down here, from the small volume, so that's the total volume, and then we would subtract by the little volume like this, which is from here to here of, this is g of yi star radius, and then again the same delta y. So this volume is going to be, so let's write this volume 1, volume 2 equals 2 pi, the radius, pi times the radius squared, which is going to be the area of this circle, times by the delta y, which is the height, to get the volume. This is g of y. Squared delta y, and then when we subtract it, so the Vi is basically going to be V1 minus V2. So volume 1 minus volume 2, and then we end up getting a ring, which equals to basically a ring like that. Or it's just a ring like that, or a flat donut, etc. So, and that's where we get this part right here, and we could simplify it further by writing Vi as pi, and then just factoring out the delta x. So now we have this like this. This is yi star minus, this is squared actually, so we're going to have it squared, and then minus, this is going to be g of yi star squared, and then delta y. And again, now that we've set up this sub-interval volume, and I'm not going to go over, well, basically the integration, the full method, but the idea is we would take this take this small interval and sum it up to infinite number of intervals that are infinitely small, and then we get a Riemann sum, and like always we get an integral. So, and you can learn more about that in my integration proof video. So what we end up getting is a total volume of, and we write this as an integral, is going to be the integral from, and now we look at our where we're integrating from. Since we're dealing with the y-axis, we're going to go from the bottom here, which is basically negative r. So because it's at the origin of the y, I mean it's at the, so the origin is at y equals 0. So then all the way to this point, so we're going to integrate from negative r radius all the way to this top part, which is r, like that. That's this part right there. So we get negative r to r, and this is going to be pi. Put this stuff inside, like that. F of y. Yeah, this is just going to be f of y. Because again, this is going to be infinitely small, so the sample points are going to coincide because this is delta y is going to be infinitely small. That yi star is going to be yi or yi minus 1. All coincide with the same value. So this is squared minus g of y squared, and then dy, which is infinitely small delta y. And I'll write the last bracket here, dy. Write this a bit neater. So, yeah, now that we've set this up, we could just go ahead and plug the formulas in and start integrating. And again, the formulas for f of y is r plus squared r squared minus y squared. Another one is the minus for g of y. So what we end up getting is pi integral from negative r to r, and now we have, this is going to be r plus square root r squared minus y squared, and this is like that. This is all squared, so we're going to have to square this. I mean, not that. So they put the bracket like that around it. And then minus, this is going to be r minus square root r squared minus y squared, and dy like that. And then what we end up getting is now what we have to just evaluate this further. So this is going to be pi, and then just expand this out, so we get negative r to r. This is going to be, well, just FOIL this out, so this is what we'll end up having is r squared when you multiply it by itself, and then we're going to have 2r. So yeah, just make sure to learn more on foiling in my foiling video, video link below, but you should be able to get this to when you evaluate this squared function like that. And then this times itself, which is going to remove the square, which is just going to be plus r squared minus r squared. So that's all on this side, and now we have to subtract it by, I'll put a giant bracket, or a bracket like this, so subtracted by, this is going to be r squared, and then we're going to have a minus 2r r squared minus y squared. And then this last one, when you multiply it, it cancels, and this is a negative. Multiply by negative, we get a positive as well, r squared like that. And then this is going to be a dy. Now when we look at subtracting, so we have this stuff, r squared subtracted by r squared. This just cancels. 2r squared square root r squared minus y squared minus a negative, that's going to be positive. So these add up to these. These are the exact same, but add up. And this r squared minus y squared subtracted by, well, r squared minus y squared. These cancel. So all we're left with is these get added up. So which equals to pi integral from negative r to r of 4r. And then we have this r squared minus y squared, like that. Yeah, and then we have a dy. Everything else cancels out. So I'll write this more neat. So we have volume is going to be equal to 4r pi, or 4 pi r, just to make it like that. And then integral from negative r to r of, this is going to be square root r squared minus y squared dy. And now if we just recall, instead of solving this just directly using integration, we could recall that a circle, well, just a circle with the origin at the center is basically, well, x squared plus y squared equals to r squared. And then if we solve for right here for x, we have x equals 2r squared minus y squared, square root, plus or minus, but in this case, we're just dealing with a positive. So if we only look at the positive side, what we end up having is a half circle. So if that's the equation, so if we end up having this as x and y, we have a circle at the origin, like that. I'll just draw this one, but this is the positive side of it only, so we're only dealing with the positive side. So this is how the circle will look like, where the radius is again r, and r, this is negative r, this is r. So this is basically a half circle. So that's a half circle, where the right side here in terms of y is, so x equals to positive r squared minus y squared, and the left side is, well, x equals to negative r squared minus y squared. So since it's a circle and the integral of it is just the volume, so what this means is the integral from it's just an area, so negative r to r of r squared minus y squared dy is just going to be you could consider this as an area, because the volume is just the area under the region. So this is dy equals to area of a half circle. So instead of solving it circle using just more complicated techniques, such as I think possibly we'll need trigonometric substitution for this, or some other methods, we could just write this as area of a half circle, which is, well, pi r squared divided by 2. That's area of a full circle is pi r squared divided by 2 to get that. So we could replace this whole thing by, this is 4 pi r, and then this is going to be what's it called, pi r squared. Pi r squared. And then divided by 2. So what we end up getting, I'll just write it over here, there's not enough room, we get volumes equal to, I'll just write that again, so 4 pi r times pi r squared divided by 2 equals 2, and then this cancels, this gets 2, and then this is going to be pi goes squared, so 2 pi squared r little r squared and then big R, and that is our volume right there. So if that's the volume, let's just double check with what we had initially with using the theorem of Pappus. 2 pi squared r squared. So yeah, that's exact same one like that. So we just went over using basic integration, which is again much more tedious for this case, defining the volume of a torus, where you break it up into small sections, and in this case 2 equations, and then sum it up to infinity and you get all that. And as you can see, it took like over 20 minutes solving that. But for this, and instead of just using the theorem of Pappus, this is just to show you how powerful and simple to use the theorem of Pappus is, and how much time you could save, especially if you're doing an exam or whatnot. You could just use this equation. And in fact, this is actually really useful. Just the whole idea of using theorems like this to simplify the process is really useful in terms of mathematics, in terms of design, or any sort of computer algorithms you're trying to create, and realize that you could save basically thousands of computations if you could realize different patterns and shapes and use theorems such as this. And this one took like a minute or two to just write this down, as opposed to solving this using this entire method like that. Anyways, that is all for today. Hopefully you'll learn from this very interesting video, and like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another math easy solution.